Well, just for the heck of it, how many folks here work on developing ESDs? Just raise your hand. Okay, good. So I'm talking to the right audience. As Sid mentioned, I'm a range hydrologist on the grazing land team there out of Fort Worth. I work with Chuck here also at the Fort Worth Center, and Johanna and Dana Larson. It's kind of and Kim Stein, she's another range specialist there at Fort Worth. I wanted to talk today about kind of a subject that's lacking in our ESD effort, and that's the hydrology section of ESDs. Am I right? Kind of something we skim over. And wanted to elaborate a little bit on what we can do to kind of enhance that section and maybe understand it, start working with information and kind of build our knowledge base on that. And so I'm going to talk about ecohydrology considerations for ESDs. And I kind of gave this talk this morning in another symposium, and I talked about that typically in our profession, we probably don't get a lot of coursework in our academic career in terms of hydrology. Maybe you picked up a watershed class, or if you're lucky, they had a rangeland hydrology course. Not too many universities even teach it. A&M, I think, may have a course. But when I was working on trying to get a degree in rangeland hydrology out of Texas Tech, I had to go outside the Department of Range and Ecology and Wildlife to get all these courses. You know, engineering and statistics departments and stuff like that, which we probably typically don't want to do as range people, so we kind of avoid the subject, and then we end up with, well, I don't know very much about hydrology. But when you think about it, you know, water is the most limiting factor on rangeland, right? So we ought to be thinking about water in a big way. It's the main driving system in rangeland ecosystems. So that's kind of what we want to address today here. And you're probably familiar with the hydrologic cycle, where you're dealing with various aspects of the water budget. You've got rainfall, precipitation. You've got interception by plants. You've got runoff characteristics on soils. Some of the water infiltrates, some of it runs off. Some of it's intercepted by vegetation. Some of it evaporates. And then whatever does get in the soil, for example, and is actually used by plants, that's actually transpired through plant stomates. Some water goes down into deep drainage. Not a lot on rangeland, typically. And then you got subsurface lateral flows, which water may travel in a lateral path to maybe a stream or a creek or a spring, or and so think about these things when you're working on a specific ecological site. You know, how do these things function in that ecological site? So what is ecohydrology basically? Well, it's basically an overlap of ecology and hydrology, where we focus on hydrologic, geomorphology, things like that, and how that relates to hydrologic cycles in plant communities. You know, you've got all the abiotic and biotic factors in soils, in plants, and microorganisms, and all these things interacting, which affect hydrology at a spatial and temporal scale. Let's spend a little time on this. Here's some basic ideas of, if you're working on hydrology in an ESD, what are some of the things you could be thinking about? And one is obviously, you know, the big buzzword, soil health, right? How do some of the aspects of soil health change as you go from one state to another in your state transition concept for your ESD? You know, what types of factors are associated with soil health? Organic matter, right? What's the status of the microflora? For example, in a healthy ecosystem, typically are the soil fungi or the bacteria more dominant in a healthy rangeland ecosystem? Anybody know? The fungi are more of your dominant microorganisms, and typically, if that site were to be degraded, typically research is showing that the biological populations start dominating over the fungal populations. And if you look at the literature, about 95% of plant species on Earth have a mycorrhizal relationship with plants. About 5% of the plant kingdom doesn't. One plant I can think of offhand is vegetable plants like broccoli, cabbage. They don't develop mycorrhizal associations, but probably more than 95% of our rangeland plants do. So consider that they're getting nutrients and enhanced nutrients and being able to, that's why they can survive in these arid systems that are typically nutrient deficient. You want to evaluate trends maybe in runoff and sediment yield for state and transitions. We're going to go through some examples here and show you when plant community composition changes. You can expect hydrology to change, and it's not always linear. For example, if a site was degrading, don't get caught in a trap thinking that, well, hydrology is also degrading in an equal amount as plant communities degrade. I'll give you an example. The annual grassland here in California. If you have a good stand of cheatgrass and other annual grasses, it's quite an adequate cover, like say 80%, 90%, 100% cover of annual grasses. They do a pretty good job of breaking raindrop impact, and they're pretty good in terms of rainfall infiltrating into the soil, not too much runoff, and actually it's a kind of a healthy hydrologic cycle when the annual grasses are there. But what happens all of a sudden if they burn? And now you've got bare ground at any time of the year, right? I mean, it could be summer, winter. When those sites go dormant, they could burn at any time, either accidentally or most of the time accidentally. And so then you've got exposed soil and you've got no protection. But when annual grasses are there, hydrologic function is typically pretty good. So it's not like, you may have gone from native grasses to annual grasses, so the native grass component dive bomb, but that doesn't mean your hydrology is dive bombing with it. So keep that in mind as you're looking at your state and transition model, and you may be wondering, like, where can I get information relative to the type of sites I'm working on? One of them is a model which I'm going to introduce to you, the REM model, the Rangeland Hydrology and Erosion Model, and then the literature. And there's quite a bit of literature on sagebrush sites, annual grass, desert ecosystems with creosote bush, tallgrass prairie, shortgrass prairie. There's enough information around, and there actually are some annotated bibliographies on rangeland hydrology that I can provide some links to those, and you can go to those and find whatever literature you're looking for. It might not be the exact thing you're looking for, but at least give you enough information to get started. So you've got to get used to looking for literature, like start learning how to use Google Scholar, for example. And a lot of the publications you can click on and get a PDF file download for those. And for papers that you can't get a download for, you can get a library card with the National Ag Library and request the publication, and they'll send you the publication via email within 2 days. So you basically can get anything you want through the National Ag Library. So as ESI specialist, you may want to get that ball rolling and get yourself linked up with the National Ag Library, because I'd say maybe 50% chance you can download the file off of Google Scholar. The others, a lot of journals want to charge you $50 a paper or some ridiculous amount. Let's kind of go through this list. Where we talked about how do changes in vegetation affect hydrology. And then there's the opposite aspect of that, how do changes in hydrology affect vegetation. So can you think of a situation where that may be occurring? Okay. Think about also any other ideas of maybe plants altered the hydrology, and now the hydrology has been altered to such an extent that hydrology now of the site, meaning the whole infiltration capacity and amount of water that can be stored in soil, that's controlling what will grow there. Exactly. Juniper. It's juniper canopy cover starts increasing. You start losing your understory. And so now this thing's flip-flopped around. So, you know, think about how those things go back and forth. Another thing you could be thinking about is discuss the effects of plant community composition and distribution relative to infiltration runoff. Here's a big one. How do conservation practices affect hydrology and erosion? Well, are you familiar with the SEEP program and the SEEP book that came? We published a book on range and pasture where the agency contracted with scientists in ARS and universities, and some NRCS people co-authored these chapters. Anyways, under the SEEP program, the Conservation Evaluation Assessment Program, where by executive order, our agency was asked, how effective what are we getting for our money with conservation practices? And guess what? The agency couldn't answer that question. So the SEEP program was born, and we did this huge literature review that took a couple of years. And we looked at some of the main rangeland practices like prescribed grazing, burning, brush, range seeding. What else, Chuck? Yeah. Anyway, there's 6 or 7 of our practices in the book, and it got a really complete literature review in terms of the science of, you know, what are the benefits of brush management, you know, aside from just removing brush. Is prescribed grazing, can we show that prescribed grazing is actually beneficial to the landscape? Range seeding, I mean, it's a book, you know, 2-inch thick book, and I think you can get it online, and we also have copies of it at the center if you want a copy of this book. So you should definitely become familiar with this because there's a lot of information in there that you can be using to support writing your ESDs. So there's something important to get on. If you're not familiar with that publication, get a hold of that right away. What are the impacts of wildfire and intense burns on hydrology? You know, they're significant. Wildfires generally burn at times when we don't want them to burn, July, August, maybe, or even during the winter when plants aren't actively growing, so then we have bare ground conditions. But typically wildfires, and Chuck, correct me if I'm wrong, but they're generally hotter than our prescribed burns, because most people who do prescribed burns, hopefully they're doing it within a kind of a frequent cycle where you don't get this tremendous litter buildup of woody material and litter material, and maybe it's burning patches and a patch over here, where a wildfire will come through and just, you know, typically eliminate everything. And the temperatures typically get very hot, and what that hot temperature does is it creates all those volatile oils in the vegetation. Obviously they melt and they go into the soil surface and create these water repellent compounds in the soil surface. So now you've got, in addition to having no vegetation for protection, you've got what we call hydrophobicity or water repellency in the top surface. So when water hits that, it's like a waxy surface, and the water just runs right off. So you've got 2 aspects which aren't good in terms of wildfire typically. Is it's going to create a water repellent situation in your soil surface, which could last a growing season or even longer. And then you've got the bare ground to contend with in terms of erosion risks. You could look at what are the impacts of grazing intensity on your plant community, and what are the effects of, here next slide is hoof impact and compaction, on soil physical properties. Obviously, if you start monkeying around with soil physical properties like increasing bulk density, decreasing your aggregate stability by heavy hoof impact, what do you think the impact would be on infiltration? Negative. You know, there's some schools of thought out there that are promoting hoof impact as a way to increase infiltration. Have you heard about that? Is there any scientific basis to that? I hate to tell you there isn't. It's people's anecdotal observations, or that's what they think they see. And I think I'm not going to get into an argument about that, but the whole holistic idea is based around that. And if you look at the literature, and there's been a lot of literature on grazing impacts in hydrology, not one study supports that hoof action idea in terms of stirring up the soil surface and making infiltration, increasing infiltration. Especially on heavy textured soils. You start getting into clay loams and heavier, the last thing you want is to increase compaction. Where do we leave off? What is the role of rainfall interception? In heavy juniper stands, you could be intercepting 35 to 50% of your rainfall. So if you're in a 16-inch or a 10-inch, 12-inch zone here in the arid west, you go to the hill country in Texas, we got 35 inches. If you're intercepting 50% of your rainfall, you know, okay, now I'm down to 15, 16 inches. How much of that 16 inches is going to run off? Maybe 30% of that. How much is going to evaporate? Maybe another 40, 50%. So when you start doing the math, what are you left with in terms of available water for plant growth? 4 or 5 inches at the most, out of a total of 35 inches precip? So these are the kind of things you can think about if you're working in an ESD where there are woody invasive plants that tend to create a solid overstory. We also can look at rainfall dynamics, like when do you get your rainfall? When do you typically get convective storms that may give you a problem in terms of excessive runoff and erosion? Those are other factors you could be thinking about. Like I was up in South Dakota around the Pierre National Grassland, and it was a couple of years ago, and their concern was that the pastures in that mixed grass prairie up there were starting to develop a lot of gullies. You know, the ranchers noticed within the last 20 years, all of a sudden we have gullies starting to form in the grassland here, and we never had this problem before. What's going on? What's changing? So think about that. What could all of a sudden be responsible for gully formation where it never was a problem before? What would be the most obvious variable in that equation, that something has changed? Yeah, well, okay, you're halfway there. She said loss of vegetation cover. Well, the cover really didn't change. It's pretty much 95 to 100%. But we found that the species composition has changed. And it's changed from your midgrasses, like green needlegrass, western wheatgrass, blue grama, little blue stem, some of those things. And now a lot of those pastures are almost solid buffalo grass. So then we start doing rainfall simulations, and we found out if you have a stand of buffalo grass, it's like paving it over with concrete. Rainfall, during a heavy storm, runoff is almost instantaneous. Then you have the next question you want to ask, well, what is it about buffalo grass that creates excessive runoff versus these other grasses? And I'll show you some data on that a little later on some experiments we did. Try to think about that. What could be the variables associated with buffalo grass that would inhibit infiltration compared to other species like needlegrass and western weed and and grasses like that. Anybody want to venture a hypothesis? I heard somebody say roots. Stolons. Yeah, well, what buffalo grass, if you dig in and you look at the root system of buffalo grass, it's a very highly fibrous root system, top 3 or 4 inches, just packed. And what that does is that buffalo grass is able to utilize moisture very quickly because the roots are right there. There's a tremendous volume of roots at the surface. And so what they do is they quickly utilize all the available water in the surface. And what happens when you start drying out these clay soils? Well, they're very dense. And if you try to dig a hole in a dry soil with buffalo grass, it's like trying to dig a hole in a concrete driveway. It's very difficult. If you were to move over a couple feet in maybe a stand of little blue stem, same soil, no differences in soil component or anything like that, it's fairly easy to dig a hole. So if you're working in an area in this short grass, I challenge you to go out and do that. Just check it out for yourself. Another aspect about buffalo grass is that a lot of grasses, as I mentioned, they're associated with specific species of mycorrhiza and fungi. Well, buffalo grass happens to be associated with fungi that create water repellent compounds. Which, what does that do? Well, that helps reduce infiltration and increases runoff. So what would the advantage be to buffalo grass to modify a site where it would create a droughty condition in and around itself in rangeland? Is there an advantage to buffalo grass to do that? Exactly. It's the way it has developed its competitive edge in the ecosystem. It creates a droughty environment. Blue grama doesn't like it that dry, so blue grama starts receding, and then buffalo grass becomes a dominant. And as long as buffalo grass is there, it maintains that more of an arid, droughty situation, which it can tolerate, but other grasses can't. So then you might ask the question, well, what factors come into play when buffalo grass recedes and maybe blue grama comes back into the stand? How would that happen? Okay, think about buffalo grass as a sod-forming grass. Blue grama is more of a bunchy, but it'll become sod-forming if it's overgrazed. But think about, there's one factor that blue grama has over buffalo grass that would enable it to compete back with buffalo grass. Any ideas? Which species is taller? Blue grama. I mean, blue grama can grow 24 inches in a really good site. What's the max height of buffalo grass? 6 inches maybe at the most? Well, there's the competitive edge for blue grama, is shading. So you get a couple really wet years, blue grama gets a little bit of foothold, starts shading out the buffalo grass, and then there's the transition, moving over more to blue grama. And just think about it. How long have these two species evolved together in that rangeland ecosystem? Any ideas? Forever? How about a couple 100,000 years? They've been playing this game back and forth, so they have it down. So think about things like this when you're working with your plant ecosystem, you know. Why is there Threon in this stand? What happened? How did Threon come to be, you know, versus it starts replacing little blue stem or Kentucky bluegrass invasion in the mixed grass prairie? What factors are associated with that event? I mean, almost every range ecosystem has a problem species. And you start thinking about that species and what causes it to have a competitive advantage? Is it resilient to grazing? Threon grass is resilient to grazing because it has silicaceous cells. It's a C4 grass. versus most everything else in the northern Great Plains are C3 grasses. And so ask yourself, how could, well, if most of your C3 grasses in the northern Great Plains evolved with grazing, therefore, and they're grazing tolerant, but they can't tolerate persistent heavy grazing over a long period of time, or they start diminishing from the stand. But then all of a sudden 3-on grass appears in a stand, and ask yourself a question: did that 3-on grass evolve with those? How can 3-on grass develop this grazing resistant trait, silicaceous cells, when the other grasses didn't? And then you maybe ask another question and say, well, did 3-on grass really evolve in that ecosystem, or did it just come in during maybe a warming trend? After the glaciers receded, 3-on grass moves up from Texas and Mexico and migrates north. The glacial period's over, yet 3-on is still there. But it didn't evolve with those cool season grasses. It just came up through some other big climatic interlude, like global warming or something, right? So I mean, think about some of these different things as you're working with your plant ecosystem. Okay, back to hydrology. We talked about the microphytic cryptogamic component. I think as you go more west, you start finding more cryptogamic across Utah, Idaho, some of those cool season bunchgrass communities typically used to have cryptogamic components. They may not anymore. So you need to kind of do some detective work and figure out where cryptogam's part of the natural ecosystem. And they're very susceptible to hoof impacts, so that's why a lot of them are gone and you don't see them anymore. But they did cover the interspace in bunchgrass communities in the Intermountain West and protected that interspace from wind erosion. The mosses and the lichens. Okay, one thing you should be really aware of when you're thinking about hydrology and the ESD concept is to think about the water budget. And this is a typical water budget equation that you would see in an introductory course in watershed management, where you're looking at the different components that add up to or subtract to the soil water storage. For example, precipitation is a positive toward water storage, but interception is a loss. So I colored those. They're supposed to be red. They don't look very red. Runoff is another negative that pulls water away from your whatever water is available in terms of storage. Groundwater flow, that's moving beyond the plant roots, deeper into the soil. Evaporation, and then transpiration obviously is when water actually is available to the plant and actually goes through the roots and up through the plant ecosystem and back through the stomates. Typically in hydrology they put evaporation and transpiration together and call it evapotranspiration. So one little fact that you need to know, and it's not in your test, is when you think about the available water that actually gets into the soil and is available for plant growth, so you're looking at evaporation, a certain percentage of that water is evaporating via solar radiation, and then whatever water stays in the soil long enough is actually uptaken by roots. When you put those two together, what percent of the whole water budget of the site is used in the ET process? Anybody have any ideas? How about 95% of your water is ET? That's water that was in the soil available. I don't know what percent of that 95%. It could vary. What goes up is evaporation, depends on what's going on with the solar radiation. But both of them together are typically 95% of the water that actually makes it into the soil goes back as evaporation and transpiration together. So it's a huge percentage of your water budget. Okay, what are the dynamics of the water cycle and the hydrologic budget on a particular ecological site? We're going to look at that here just as an example. How many people are familiar with the National Range and Pasture Handbook? Okay, well, Chapter 7 is a chapter on range and pasture hydrology, and this is just a page out of the handbook. And by the way, we're updating that chapter. And there's 3 stands here. The first stand is a fairly intact site, or you would say this would be maybe a reference community in a tall grass prairie where you have a good complement of your tall grasses. And here's a site where Kentucky bluegrass and smooth brome have invaded the pasture due to heavy use over time. And this is an actual site from Wahoo, Nebraska. So I didn't make this up. And so we went from tall grass to almost a whole complete stand of Kentucky bluegrass and smooth brome. And then we had another stand where the Kentucky bluegrass and the smooth brome flip-flopped in terms of their percentage in the stand. And so I developed kind of a water budget for each of these stands. And you start looking at, for example, infiltration. I mean, surface runoff typically would be 20% of your entire water budget could go off as runoff. But when you look at Kentucky bluegrass, upwards of 45% of your water could run off. And then this other stand here with smooth brome and Kentucky bluegrass, what is that, 30%? So you might ask yourself, well, why would there be more runoff in a Kentucky bluegrass stand compared to, say, these native tall grass bunch grasses? Any ideas? It's a sod former. So you see what I'm getting at? We had a discussion of buffalo grass is a sod former, Kentucky bluegrass is a sod former, smooth brome is a sod former, and we found through doing enough rainfall simulations over the last 30 years that sod forming grasses are always associated with higher runoff potential than bunch grasses. That's just it's kind of a law now that we see it over and over and over as we travel around the country. We see it in North Dakota. We see it in Nebraska. We see it in Texas. So when you start, your stand is going from more native bunch grasses to even a native sod former or an introduced sod former. A red flag should go up and tell you that my hydrology is changing here, and that's going to affect productivity. It's going to affect everything on that site. Here's another example of a study that was done in the Rio Grande Plains in Texas on a sandy loam site where they set up some lysimeters, and they looked at the difference between bare ground, grass interspace, and shrub clusters. And they looked at runoff potential and deep drainage. I think it's interesting to note there was no deep drainage in the shrub clusters, but probably not a real significant difference in runoff between the shrubs and the grasses. But look at the difference in deep drainage even within bare ground. I think that's pretty interesting. There's a lot of runoff, but there was also a lot of deep drainage. And then this is kind of a comparison of the evapotranspiration among the 3. So not much difference between the grasses and the shrubs here. And this was mesquite. This wasn't juniper. So this is a deciduous shrub. But anyway, that kind of data exists in the literature. And you can use that in trying to get an idea of how hydrology may be changing as plant communities change in different states, especially if you're working with shrubs like juniper and mesquite and stuff like that. Good question. Typically, number one, if you're in a sagebrush stand with a blue bunch, wheatgrass, Idaho fescue, Poa secunda type interspace, but you still have your sagebrush, but you've lost your native grasses to, say, Medusa head, cheatgrass, and so forth and so on, I always say that if you're doing a rangeland health assessment for hydrologic function, you're already at moderate departure. okay? I don't even go through the indicators. I know I'm at moderate departure. And why? Why would I be that far away from the reference community just by losing my native grasses in the inner space? Right? And what happens to cheatgrass over the winter, through the winter? Yeah, but even before it starts germinating and growing again, say you go from June all the way till December. What's happening to cheatgrass over those months? It starts breaking down and decomposing, right? So you might not have much cover, say by October, November. A lot of that cheatgrass may have dried up, blown away, who knows? So you basically have bare ground. You may have bare ground for a couple of months. So there's bound to be a rainfall event or something that occurred at some point in time when cheatgrass was basically not there to protect that soil surface. So what happened? Some of it blew away. Some of your soil washed away. You've oxidized your organic carbon because solar radiation is heating up the soil to a warmer temperature. Just think about all those factors that over, say, 50, 60 years even, say maybe 100 years, cheatgrass has been in that ecosystem. What could happen over 100 years to the top 2 inches of your soil? There's a lot of things that could happen that would erode that away. Just to alert you to the fact that I think in most rangeland ecosystems you need to be thinking about conservation practices and their effect on hydrology, specifically prescribed burning and wildfire. This happened to have been a wildfire in July. That's me collecting data. And then, and 1 year later, look at the vegetation response. This was a mountain big sagebrush Idaho fescue site in Denio, Nevada, 6,000 feet elevation. A pretty incredible response of the vegetation just in the first year. So if I were writing something up for this site, I might want to talk about that typically if you have the moisture, your vegetation is going to respond pretty quickly. And what we were doing here is I was looking at plant diversity between the existing stand before the fire versus the plant diversity after the fire. Excuse me, go back. I should have put a picture up there of a site that wasn't burned, but typically we maybe had 12 species in the pre-burn, unburned mountain big sage community. I have it upwards of 35 or 40 species in this stand. And they were all native species. Just things that fire, you don't see a plant or species for 25, 30 years, and then after a wildfire or a prescribed burn, that species just shows up. And Chuck, you probably teach that in your prescribed burning classes. It really invigorates the forb population. Because a lot of forb species, seed germination is enhanced by smoke, which I think is really odd, but it's true. I wanted to go through an example of a site where I've done some rainfall simulations in West Texas, just to kind of lead you through a discussion. We're going to look at a state in transition model, and I've done rainfall simulations on these different states, and we're going to kind of look at that and show you some of the different things that you could perhaps be talking about in a respective ecological site that you're working on. This is an interesting place at Muleshoe, Texas. It's a National Wildlife Reserve. There's 3 big saline lakes out there, and they're home to a lot of waterfowl during the winter, like sandhill cranes and pelicans, and it's a very unique place. And what's even more unique about it is it's host to pretty much a pristine blue grama shortgrass prairie. because not much grazing is ever, very light grazing. They do graze it, but it's at a very light level. And so this is an ideal place to find good reference historic plant community sites for shortgrass prairie. And it also has prairie dogs, which are highly disruptive, as I'll show you. So if you look at a typical shortgrass prairie state in transition, and this is more simplified just for the demonstration here, but you have your dominant blue grama with buffalo grass as a subdominant grass, and within this you could blue grama and buffalo grass. The composition goes up and down depending on the grazing pressure and the climate, and they go back and forth. Okay, so you introduce heavy grazing over a longer period of time. You start diminishing the blue grama. The blue grama is less resilient to grazing than the buffalo, so the buffalo grass starts becoming more of a dominant, and basically it spills out of this state into a different state down here. And then this state also develops in response to prairie dog towns, which are down here in their own state, where when prairie dogs abandon their towns, or they die off because of the plague or one reason or another, what typically happens is the first species that comes back, and typically these prairie dog towns are dominated by Texas tumblegrass, 3-on, a bunch of grasses that are basically non-palatable. But what happens is, over time, the buffalo grass is probably the first other native grass that responds and starts creating almost a complete monoculture around the prairie dog towns. And then you occasionally have clumps of broom snakeweed, which is maybe the 5th state within this whole idea. So there's the basic state in transition idea. But let's look and see, this is what the sites look like in reality. Here's your reference community. Here's kind of where you start getting more of a mixture of blue grama and buffalo. You start getting a little more interspace. Here's your prairie dog town. And then these are your buffalo grass stands that start colonizing around these abandoned prairie dog towns. And so we did rainfall simulation experiments in each of these different plant communities, and this is still within the context of the same soil component. Okay, it was a Bertus loam soil, and we mapped them, we checked them, we did profiles. They're all the same. We're not changing component here, so we're controlling the soil as being similar during our rainfall simulation experiments. And we also collected other data in each of these states. Here's your blue grama state, and here's your tumblegrass 3-on, which is the prairie dog town. And you can look at just, I'm not going to go over the whole table, but just kind of scan through here and look at the differences in production among these different states. And root biomass, 10,000 pounds per acre in the top 4 inches compared to 1,700. Root shoot ratios, canopy cover, organic carbon. With these kind of differences, wouldn't you expect there to be some change in hydrology? And once you're in a situation like this, you're starting to get into that example that I talked about on the first screen, where hydrology now is controlling vegetation because of the limitation of water. And until that gets turned around, it may take 50 years, 25 years, who knows, quite a long time for those prairie dog towns to recover back into some a resemblance of blue grama and buffalo grass. Okay, so here we're adding one little more piece of information. From the simulation experiments, we found that our infiltration capacity was highest in this community. Less as you started getting more and more buffalo grass, the infiltration capacity decreased. As you went more to solid stands of buffalo grass, it decreases even more. As you go to a prairie dog town, it's the lowest infiltration capacity. But then we have a stand of this perennial broom snakeweed over here, And it had as high an infiltration capacity in the broom snakeweed as did the pristine blue gramosnake. Okay, that threw me a curve. What would cause that? If you're familiar with broom snakeweed, you know, it's kind of a half shrub type plant, maybe 20 inches tall. It's evergreen. It tends to drop when it drops leaves, they tend to build up a little shrub coppice underneath the plant, so you have a little mound of litter under there. And when the wind blows silt particles, the silt accumulates under those snakeweed plants, so you start building up this little mound of higher silt, higher organic matter because of these leaves, these evergreen leaves. If you ever looked underneath a juniper tree, at that duff layer under the juniper, it could be 5-6 inches deep. The same thing over time with these broom snakeweed stands. So it was just like a big sponge underneath that broom snakeweed plant. And broom snakeweed also has tap roots compared to fibrous roots like grasses. And tap-rooted plants tend to modify the soil around it where water starts funneling down along the length of the taproot. So, you know, there was a reason for that, but it was very surprising to find that infiltration capacity was as high here as it was here. So the point I'm trying to make is don't always assume that the hydrologic cycle is deteriorating along as maybe a plant community might deteriorate, okay? The example I used before was annual grass. Just because there's an annual grass out there, if annual grass is actually there and providing cover, it does a pretty good job of protecting the soil surface. But then it's susceptible to instant removal, isn't it? Okay, one next step. We use the rangeland hydrology erosion model, and this is a tool that we're going to link to the new ESIS template that's being developed right now for developing your ecological site descriptions, where you can start using this tool to explore hydrology and erosion dynamics. It's a very simple tool. You choose your climate. There's a map in the site. You pick your nearest climate station. You can adjust the climate based on elevation. You enter your soil type, your surface texture. You enter your slope percent, whether your slope is concave, convex, sigmoidal, uniform. You can put that in there, the slope length, and then the cover. What percent cover of sod-forming grasses, bunch grasses, forbs, and shrubs, and then what percent of rocks, lichens, mosses, and litter. And those are the basic inputs to the model. And it will calculate and do some predictions on runoff and erosion and soil detachment. So I use values out of the REM model here to show what the REM model would say in terms for this plant community. So this is basically a 17-inch annual precip site, about 3 inches of runoff in an average year. Soil loss is very low, 0.6 tons per acre. Come down to here, the runoff increases a little bit, soil loss increases to a little bit over a ton. And then get down here into the buffalo grass. Runoff is almost double what you would have in the bluegrass, this pristine site here. And then you get into the prairie dog town and you've got 7.5 inches of runoff compared to 3 inches here, and your soil loss is almost approximating 3 tons an acre. Now, I don't care about the numbers. I just want you to kind of look at the basic trends of increasing and decreasing. That's more important than these numbers. These numbers are just relative values. And whenever we model, even the experts who develop these models saying these numbers could be 100% off. go up and down 50% each way. But I just want you to look at the basic trending of runoff and soil loss as you go through this state and transition model. And And so this tool can be pretty valuable in helping you explore the dynamics as your plant communities may change. If you're working in a juniper site and you're starting to get more juniper dominance, or whatever site you're working in. So the new ESIS tool will have links to this, and we're also going to, I think we're going to have an idea of where if you're developing a state and transition model here, and you want to run REM for this state, there'll be a link button, and it'll take you to REM, and we'll already give you some cover values and some of the other slope values that are typical to this site. So you can use those built-in numbers, run the model, and then you could also change the numbers and play with it depending on what you want to do. So hopefully this tool will help you formulate some ideas about hydrologic changes as you go from different states and transitions in your state and transition model, especially where you have really significant changes in plant species. Yes, and we can send the link out to you, but the easy way to get to this is just type USDA ARS Tucson, Arizona. That's where the model is hosted on their website. And you'll see a big button, click on the REM model, RHEM, and you're there. So USDA ARS, Southwest Watershed Research Center in Tucson, Arizona. And it's really easy to use, and start playing with it. And so basically that's my presentation for today. Any questions?